Hi, good afternoon to everybody. Can you please all sit down so that we can start the question and answer session? So there are about 8 to 9 questions. I'll start with an interesting question asked by Ananya Hegde. Who is Ananya Hegde? Can you please stand up? Okay. You can come in the front so you can get your answer. Her question is, I have heard about Schrodinger's cat mind experiment, and today you have given an explanation relating it to the state of the particle of light. I wanted to know how else does this mind experiment can be used practically in our day-to-day lives?
Yeah, this is a question about how you can use the strange properties of quantum physics to achieve tasks which cannot be done by classical systems. The Schrodinger cat story is a kind of metaphor to explain that in the quantum world, a system can exist in different states at once. Yeah, here. So in quantum physics, a system can be in state superposition. You can have a quantum particle can be at 2 different places at once, or an atom can be in 2 different states at once. And this property is completely different from what in the ordinary world. So if you could use this superposition, you could do things that you cannot do with usual machines. For example, in a computer, the transistors in a computer are either coding for 0 or 1. In a quantum machine, the computer could be in a superposition of 0 and 1, and this gives a much bigger space to store information and to process information. So the idea is that one could use the notion of state superposition to do things which cannot be performed with classical systems is a very active field of research now to develop new ways of computing or new ways of communication. It's a different way to look at computing, communication, or measurement using the properties of quantum physics. Now, why is it called this system called Schrodinger cats? Because Schrodinger, when these concepts were first established, imagined an experiment in which an atom in a superposition of states would be interacting with a cat. What he imagined is a big box. You put a cat in the box and you prepare an atom in 2 different states at once. If the atom is excited, nothing happens to the cat. If the atom goes to the lower state, it emits a photon, and the photon can trigger a process which kills the cat. Now, if the atom is at the same time excited and not excited, then the cat should be at the same time alive and dead. Of course, this never happens in the real world because you cannot have big systems in state superposition. So Schrodinger imagined this story just to emphasize, to illustrate the fact that if the quantum world could be translated to the macroscopic world, very strange things would happen. So it's just a metaphor, and since then, the states that you can manipulate in this way are called Schrodinger cat state, but it has nothing to do with a real cat. It's just an image. Okay. Thank you.
Did you get most of the answer?
Yeah, I understood.
Okay.
Yes.
How old are you?
I'm 16 years old,
Okay.
and I study in Little Rock Indian School.
Okay.
Little Rock Indian School.
Okay.
Yeah.
Okay. Very good. Thank you. It's a good question.
That was did most of you understand the question? Yes or no? Did most of you understand the answer? Can I ask one of you to come back here and answer? Okay. All right. The next question is from Vrashti Mallya. I have heard that to travel into the future, we have to travel at a speed faster than light. Is something even remotely close to that possible?
No, I don't think we can travel faster than light. In fact, the theory of relativity, which has been developed by Einstein in 1905, shows that nothing can go faster than light. If you approach the speed of light, then strange things happen. For instance, if you have two twins, one who stays on Earth and the other one who travels with a very fast rocket and comes back to the Earth, then according to the theory of relativity, the guy who is doing this travel will be much younger when he comes back than the other one. So it's one way to travel in the future. It means that if you can do that and come back, you will see what will happen in the future, because you could survive most of the people who have stayed behind. But of course, we are very far from doing that, because for that you would have to reach a velocity which is a large fraction of the velocity of light. For instance, to go at 200,000 kilometers per second. And this is impossible according to all foreseeable technologies. It would need a huge amount of energy. In fact, there is a small effect which is already visible. If you travel by plane a lot of time, and if you accumulate the time change due to this traveling plane, you may win a few microseconds. So maybe I'm a few microseconds younger than I would be if I did not travel so much by plane. But a microsecond is not something which is very important. So there is an effect, and clocks, it's very important for clocks. For instance, you all know about the GPS system, the system which is used to localize oneself on the surface of the Earth with a very high precision. The GPS is a system of satellites going around the Earth, and each satellite has an atomic clock, a very precise clock, and this clock sends microwave pulses which are detected by the machines, the small machines that you can buy, and by triangulation you can find your position on Earth. But for that you need to make corrections for the kind of effect I described, because the clocks are so sensitive that if you did not correct for relativity effect, for the fact that the clock don't tick at the same rate in the satellite that they do on Earth, then your GPS system will be off by kilometers, completely useless. So you really need these relativistic corrections in precise devices. But of course, this does not mean that you travel in the future. And traveling in the past is even more impossible, because if you could travel in the past, you could act on facts which have not occurred. For instance, you could come back in the past and kill your grandparents, which would make the system completely meaningless. And so you would violate what we call causality. Traveling in the past would violate causality.
Okay. All right. Thank you very much. The next question is, sir, you spoke about supercooling. Is there a method called superheating as done in Hadron Collider? If so, could you tell us about its application, especially in atomic physics?
Okay. First of all, to answer this question, I must first talk about temperatures to give you orders of magnitude. If you look, the temperature measures the degree of motion of atoms. The higher the temperature, the faster the atoms, or the faster the vibrations of atoms in solid media. Inside stars, the temperature is millions of degrees. At the surface of the sun, the temperature is 6,000 degrees. On Earth, the temperature is 300 degrees. In fact, I'm talking in absolute degrees. Not in Celsius degrees, 300. And when you cool with lasers, you go down in temperature to temperature which are much less than 1 degree, even less than 1/1,000,000th of a degree. In fact, we are talking about billions of 1 degree, very, very cold matter. And this is done with lasers. But if you just use the fact that the laser can slow down atoms by exchanging momentum between atoms and light, you can cool matter with lasers. On the other hand, you can also use laser to heat. For instance, if you focus a laser beam on a sheet of metal, you will evaporate the metal, you will make plasmas, you will make very hot media. And in fact, there are very powerful lasers, megajoule lasers, which concentrate in a very short pulse of light a huge amount of power, which are used to heat at millions of degrees very small pellets of deuterium, the deuterium atom, which is an isotope of hydrogen. And you reach temperatures which are so high that we hope that nuclear reactions can be ignited. So you can reach millions of degrees by concentrating the power of lasers on a very small spot. So you see that lasers are really fantastic. They can be used to heat at the temperature which are inside the stars and to cool to temperature which are the coldest temperature in the universe. And if you look on a logarithmic scale, on powers of tens, you can explore a domain going from 10 minus 10 degrees up to 10 to the 6 degrees. You have 16 orders of magnitude of temperatures that you can explore using the properties of lasers.
Is the mechanism of laser cooling the same as the mechanism for laser heating, or the mechanisms are extremely different?
No, the mechanisms are very different. The cooling is not destructive. In the cooling, you use lasers which cannot absorb the light, but which you use lasers which absorb the light and re-emit. The atom absorbs and re-emits the light, and it stays. The atom is not destroyed. It's external degrees of freedom which are modified until the atom is put to rest. Whereas for heating, you destroy the atom, you ionize the atom, and you separate the constituents of the atom into elementary constituents. So it's a much more brute force process. It's much more related to the process happening in an accelerator of particles, where you smash the components between each other and destroy and just look at the end products. In the cooling process, it's much more gentle. You just keep the systems there. You just modify the velocity at which the atoms move.
Who discovered that lasers can be used for cooling an atom?
There have been several people who can claim that. The first, just a few years after the laser was invented, there were proposals to do that by a guy from Bell Labs called Ashkin. So Ashkin wrote some theoretical papers, but at that time the lasers were not precise enough to do that. You need to have very powerful and very monochromatic lasers, because you want the laser to have a spectrum which is adjusted to do exactly that and not to destroy the atoms. So it took, after the first proposal, it took about 15 years until the first demonstration experiment could be done by people like Steve Chu or Bill Phillips, who shared the Nobel Prize with my thesis advisor, Claude Cohen-Tanucci.
I see.
So, and this gives you an idea also about the time scale of research. Before the time we make a proposal before the time you make a proposal and the time you can achieve the experiment, very often you have a decade, 10, 15 years, even more, because you need technological developments and you need a lot of efforts and a lot of work to achieve that. So it's very important in basic science to have a lot of time to develop one's ideas.
Okay. Are you guys understanding the answers? Yeah? Do you see, when we ask a question to professor, he doesn't even bat an eyelid before he answers the question. Do you see that? That shows the depth of knowledge, okay? The depth of understanding a concept so beautifully. If I ask a question to any of you, I'm sure you'll say, I'll go home, read the book, and come back, right? So this is something that is what is necessary when you want to become a Nobel laureate. The depth of understanding is extremely crucial, right? So the next question, does electron have constant density?
This is a difficult question. The electron, in fact, is a point-like particle. It has a small mass, a mass much smaller than the mass of the atom. It's about 1/2000 the mass of the lightest atom. And it's very difficult to define in classical terms its dimensions. So you could, there is a classical radius of the electron, which is 10⁻15 centimeter or so. So if you could, you can in theory give a density, but it has no meaning. All the properties of the electron are defined by its electric charge, its mass, and its magnetic moment, its spin. And with these three quantities, the mass, the charge, and the magnetic moment, you can understand all the properties of the electron.
So the classical density is mass over volume is not applicable in quantum physics.
No, it's not relevant for to describe the electron. It's you could use it. For instance, the proton, which is a nucleus, has a diameter which is of the order of 10⁻15 meters. That is 10⁻5 times the size of an atom. For the electron, you have a classical description. If you take what is called the classical radius of the electron, you find a result that I don't remember, but it's not a quantity which is useful for a direct experiment on the electron.
Who asked that question?
Okay.
Who asked this question?
Yes, the guy.
Oh.
Yeah.
Did you get your answer? Yeah?
So,
Does stopping light violate Heisenberg's uncertainty principle?
does
Stopping light violate Heisenberg's uncertainty?
Yes, I did not talk about stopping light. What I talked about using light to stop atoms. Now, there are other experiments in which people stop light. In fact, what happens is that you can send light through an atomic medium, and the light can be stored in the medium for some time and then released at a later time. So there is a way to slow down light beams into material systems. But this never violates Heisenberg uncertainty relations. These relations state that it's not possible to measure simultaneously with arbitrary precision the position and the momentum of a particle, for instance, or to measure with arbitrary precision the amplitude and the phase of a light beam. And this is never violated. You can make experiments in which you make the system more sensitive to position and then less sensitive to momentum, or the opposite, depending on what you want to measure. You play around with the Heisenberg uncertainty relations, but these are fundamental relations which are not violated. In fact, quantum physics is a theory which has never been violated so far. It does not mean that it will not one day find some limitations, like Newton's equation, which after 300 years were modified by Einstein. So maybe one day the equation of quantum mechanics will be modified and transformed into something which will be more general. But up to now, this has not happened.
Who asked that question? You asked the same question?
Yes, yes.
Okay. Do you think this question is your next Nobel Prize experiment you want to do?
No.
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 No, okay.
Okay.
It's clear. The answer was very clear.
Explain what magnetic spin quantum number for electron is it?
That's a tough question.
I see.
Electrons and nuclei carry an intrinsic magnetic moment. They are like a small magnet which is carried by the atom. And this magnet is associated to a kind of internal rotation. If you have an electric charge, if the charge rotates, it creates a rotating current which produces a magnetic field. So there is, for the electron and for the proton, there is a classical image which may explain the magnetic moment. This image does not work for neutral particles, which also may have a magnetic moment like the neutron. So it's an intrinsic quantum property. And what is striking is that if you do an experiment and want to measure the magnetic moment of an electron, for instance, you will, along a given direction, you will find it either pointing in the corresponding direction or opposite. And you will never find it in any other direction if you make this measurement. You will find plus or minus the same quantity. This means that the magnetic moment is quantized in the same way as the energies in an atom are quantized. And one says that this particle has what we call a spin 1/2. A spin 1/2 has two possible positions. Other particles have larger spins. The spin 1 can be +1, 0, or -1 according a given direction. So these are properties which cannot be described in classical terms. You need quantum physics to understand deeply what it means, but it's a very important property. As we will see in one of the lectures I will give, the nuclear magnetic moment is a probe which we all have inside our bodies. And in magnetic resonance imaging, we can make a picture of our bodies inside by measuring the density of magnetic moments inside different organs, in the brain, in the lungs, for instance. And we get very precise pictures which are based on the detection of precessing magnetic moments of matter inside our bodies.
Thank you. How did they measure the speed of light as 3 × 10⁸ meters per second?
That's a very interesting question because it has a very long history. In fact, the first person who tried to measure the velocity of light was Galileo. All of you may have heard of Galileo, the famous Italian scientist of the beginning of the 17th century. So Galileo had a very simple idea in mind. He stand outside with a lantern and had one of his assistants several kilometers away on another Toscan hill, and he uncovered his lantern and asked the assistant to do the same thing, and he wanted to measure the time it takes for the light to go back and forth over 7 kilometers. And the experiment failed. It failed because the light goes so fast that it took only a few microseconds to go back and forth. And of course, our perception is much slower than that. The only thing he could measure is the reaction time of his assistant, and he just could show that the light was going very fast. Then the same Galileo, a few years later, developed the first telescope, what is called the Galilean telescope, which allows you to look at stars and to look at planets. And Galileo discovered the satellites of Jupiter. He looked at Jupiter through his telescope, and he saw that around Jupiter you have satellites going around. Now we have, maybe I think there is something like 10 satellites. At that time he could see 4 of them. And in fact, you can do that if you have just a regular camera, and you put the camera on a tripod, and you aim at Jupiter and you have the right exposure time, you will see Jupiter with these satellites. So this seems to have nothing to do with the velocity of light. But in fact, a few tens of years later, there was an astronomer in Paris called Rømer, a Danish astronomer, who used the observation of the satellites of Jupiter to make the first estimate of the velocity of light. What happens is that when the Earth is going around the Sun, for half of the year, the Earth is going away from Jupiter. And during the other half of the year, the Earth is going back towards Jupiter. And what Roemer looked at was the eclipses of the satellites. He measured the time at which one of the Jupiter satellites who was behind Jupiter reappeared on the other side. And what he noticed is that during the 6 months the Earth was going away from Jupiter, the reappearance of the satellite took more and more and more time. And during the 6 other months, it took less and less and less time. And when he measured the accumulation of these delays, he found about 15 minutes. And he assumed that 15 minutes was the time it takes for the light to go across the diameter of the Earth's orbit around the Sun. So, but then one had to know what was the diameter of the Earth's orbit. And for that, in the 17th century, there were people who were going from Europe to America, and they aimed at Mars from France, for instance, and from Guyana in South America. And Mars appeared at slightly different angles because of the different position. It's a very small angle, but by measuring this angle, knowing the distance between Paris and South America, you can estimate the distance of Mars. And knowing the distance of Mars and knowing the laws of the Kepler's law for the motions of planets, you can extrapolate the diameter of the Earth's orbit. And from all this measurement, one could estimate for the first time the velocity of light and found a result which was not 300,000 kilometers per second, but quite close, 250. So this was in the 17th century, and I think this story is very interesting for different reasons. First, it shows that Galileo was wrong when he tried to measure, but he developed an instrument who allowed other people to measure later. And this is the surprises of basic science. You do something, you don't know what it will be useful for, and somebody else make it useful for something else. And it also shows that to make a measurement like the velocity of light, you need to have a good knowledge in optics, you need to have a good knowledge in mechanics to understand the motion of the planets, and you need to make measurements like make astronomical observation at different points on the Earth. So this was 17th century. Then one had to wait until the 19th century to improve that. And the guy who improved that was Fizeau. It's a French physicist who did the experiment of Galileo, but with modern technology. He used a dented wheel, a wheel rotating very fast with a light source behind. And this wheel was sending pulses of light. Each time an opening of the wheel was in front of the beam, a pulse of light was going out. And 7 kilometers away, he put a mirror. And so the light was reflected and coming back. And during the time the light was going back and forth, the dented wheel had turned, and he measured exactly when the delay was such that the light was coming back in the next opening of the wheel. And knowing the speed at which the wheel was rotating and the distance, he could make a precise measurement of the velocity of light. So it was like Galileo experiment, except that instead of an assistant, he used a mirror which reflects immediately. Nice. And he could do it very fast because he had the technology of rotating wheels of the 19th century. And then lasers came, and with lasers you can measure the velocity of light with a huge precision. So precise that now the meter is defined as the distance that the light travels during a given amount of time. So you see that this has been fantastic developments. And also I want to make a last remark. Fizeau made his measurement in 1860, I think. 4 years later, Maxwell, a Scottish physicist, wrote the equation describing the propagation of electric and magnetic fields in space. And from these equations, he could derive what was the velocity of this electromagnetic wave. Nobody knew it was light. And he found a result which was in almost perfect agreement with the measurements that Fizeau had made. And then he said that cannot be a coincidence. It means that light is an electromagnetic field. And this was maybe one of the most important discoveries in physics, because this has led to all the modern technologies that we know about. So the measurement of the velocity of light is really a central point in physics. It's a very important measurement, and it has a lot of different applications and consequences in applied physics, and of course also in fundamental basic science, because the velocity of light is the absolute limit of propagation of information.
Who asked this question? Who asked the question how to measure speed of light? Can you? No? Okay. Anyway, did you guys get the answer? Did you know who was the first one who tried to measure speed of light? So you could understand. Fantastic. So they have understood what was good. Who was the last one who tried to measure speed of light? The French physicist. Fizeau. Okay. Is time machine possible using Einstein's theory of relativity?
I think I answered this question earlier. It's, what Einstein showed is that the rate at which time evolves depends upon the observer, and you can use this in principle to build a time machine in the future if you can go fast enough, but not in the past.
Okay. Trisha, who is Trisha? Is here? Now. Is the many features of photon still to be discovered? Any idea about it using the present technologies?
Okay, this is a good question. In fact, the photon is a quantum of the electromagnetic field, and the electromagnetic theory, the quantum theory of the electromagnetic field is very well established. So I think that in theory, we know exactly what the photon is, and we know what these properties are, and we have measured with high precision in quantum optics. We measure with very high precision the properties of photons. Now, this does not mean that there may be some applications of the photon and the quantum properties of photon we have not thought about yet. I know, for instance, that if 20 years ago one has been said that you can use what we call entangled photons to communicate in a secret way, to be able to send messages which cannot be deciphered. This is called quantum communication. This was not understood before researchers discovered that, let's say, about 20 years ago, and now we are trying to implement this and develop this. So maybe there are other ideas which are waiting to be discovered, and this will be your task in the future generations. Even if a tool is well understood in principle, it does not mean that there will be no application of this tool. I think of this a little bit like a chess game. It's not because you know the rule of the game that you have understood all the possible moves on the chessboard. In physics, it's a little bit like that. You have two kinds of physics. You have the physics which try to discover the rule of the game. For instance, before Maxwell, one did not know what electricity and magnetism were about. Maxwell discovered the big rules. Then quantum physics, another set of big rules. More recently, when the Higgs boson was discovered, it was another set of fundamental rules. Now, what we do in quantum optics is different. We know the rules because we apply quantum physics, but we try to use these rules to put nature in situations which have never been tried or tested before. And there are many, many such situations which can still be discovered or revealed by experiments, and this is what we do. So my answer is that the photon is well understood, but what we can do with the photon is not a solved problem, is not a problem which may not have other solutions, other applications, other fruitful devices coming from it.
What is the difference between quantum physics and classical physics?
there is a big difference. The laws are, the way you look at nature is not the same. In classical physics, an object has well-defined properties, and whatever you do on the system, if you measure it, you don't perturb it, or you can, at least in principle, perform experiments which do not perturb the system which you are measuring. In quantum physics, the situation is much more subtle. The system can be in different states at once, as I said, and when you perform a measurement, there is a random perturbation, and the result of the measurement can take different values, and the only thing you can predict is the probability to find one result or another one. So basically, quantum physics is a probabilistic theory, whereas classical physics is deterministic. If you use Newton's laws, in principle, if I give you the initial condition of all the particles, assuming Newton's laws, you can follow the system and predict exactly in which state the system will be in the future. It's what Newton thought. It was a great mathematician like Laplace at the end of the 18th century said, give me the initial conditions and I will predict the future. Of course, this is not possible in practice, but in theory, it's possible. According to quantum physics, even in theory, it's not possible. An elementary experiment in quantum physics yields random results. And that's what Einstein summarized when he said in quantum physics, God is playing dice. And Einstein did not like this idea. Einstein thought that there was something wrong with quantum physics, and that one day one would get out of this randomness. It has not happened yet, and it's one strange thing about the psychology of scientists. You know, Einstein discovered